Dear Sir and Madam, it's my pleasure to attend the MITAB. I'm Chen from China University of Petroleum and Beijing. My title is Apprising Carbon Dioxide Geological Storage Potential in Abundant Shales by a well-tested methods. Then I will introduce my reports from the 6 parts: introduction, methodology, models, verification, results, and discussions, and with conclusions. As we know, the boom of shale gas stimulates the exploration and the development of vast shale gas reservoirs. How to exploit the residues of the depleted shale reservoirs is an important task for us reservoir engineers. Some researchers point out that one of promising ways to use these depleted shales is storing CO2. This is very beneficial to our environment. I quite agree with that. However, only a few are interested in depleted shales for safety and economic reasons. Therefore, lots of work needs to be done to better this situation. But for us, engineers, first and foremost is an urgent question needed to be solved: how to evaluate the CO2 sequestration capacity in the depleted shales. After little reviewing, we found that there are 4 types of methods. The first one is volume-based method. It's like to calculate the reservoir's volume to evaluate the CO2 sequestration capacity. This method is easy, but it have very bad accuracy. The second one is a production-based method, and the third one is a reserve-based method. The fourth is numerical models, and finally we propose a pressure-based method. The pressure refers to the wellbore pressure. We can calculate the CO2 sequestration capacity based on the wellbore pressure, because if we inject the CO2 into the formation, we can know the wellbore pressure first. With the wellbore pressure first, we can calculate the CO2 sequestration capacity. So we propose a numerical method based on our previous work. The method is based on the trilinear flow model. The trilinear flow model is proposed by the Ozeken in 2010, which is based on transient pressure. We can consider multiple factors, and it's quick and reasonable. So let's see our methodology. Our methodology including 3 steps. The first step is developing a trilinear flow model. We assume the well is injected with a constant rate, and we can consider multiple factors: diffusion, gas desorption, and permeability of stress sensitivities. The second step is solving model and obtaining pressure performance. We can use Petros's substitutions to consider the stress sensitivity effects. You can use the Steffen-Fest numerical equation to obtain the wellbore pressure. Finally, based on the wellbore pressure, we can evaluate the CO2 sequestration. We perform some sensitive analysis. We can also perform a case study. Then, let's move the models. This is our model. We can see a physical model for depleted shale reservoir with a sealed rectangular boundary. This is a multiple fracture horizontal well. It's a main production tool before the shale reservoir was depleted. It acts as an injection well for storage CO2 in the center of the reservoir. The model can be treated as 3 flow regions. You can see the right finger. We can have the hydraulic fracture, initial inner dual porosity reservoirs between the hydraulic fracture and the outer dual porosity reservoirs via the tips of the the hydraulic fracture. This is a physical model. Then we can make some assumptions. The fracture, we assume that the fracture is orthogonal and is even distributed. The gas flow in the matrix, because this region is dual porosity media, including the matrix and natural fractures. The gas in the matrix observes the Knudsen diffusion because the nanopoles. If the gas flow in the natural fracture, we think that it observes Darcy flow. The gas is a single gas flow phase. The wellbore inject with a constant rate. Then we have the outer region system, inner region system, and the hydraulic fracture system. We can assume the flow direction is a 1D flow. 1D flow and in the fracture like this, and in the inner region the gas flow direction is like this, and then outer region. For a CO2 it can flow first and then like the second arrow, and then with the final. So use this physical model, we can obtain the mathematical model. The flow in the outer region system, we can have the mass balance equation and the boundary equation. Boundary equations, and the same with the inner region system and hydraulic fracture system. The first equations are the mass balance equation. We can consider the dual porosity and stress sensitivity, and also we consider the gas desorption and absorption like this. So finally, we solve this model, mathematical model. We can obtain the wellbore pressure solution. With the wellbore pressure solution, we can enter the flowchart to estimate the CO2 sequestration capacity. They are including 5 steps. The first step is setting a constant contrast injection rate, like 10 or something, just a value. And then with this injection rate combining with the wellbore pressure, we can plot in the type curves of transient pressure. This is the second step. And then we can determine the concentrated injection pressure, namely the wellbore pressure. Generally, we set the injection pressure is lower than the rock breaking pressure. And then, with this pressure in concentrated injection pressure, we can obtain the total injection time, like this. For example, we can obtain the time. With this time and the injection rate, we can easily obtain the CO2 sequestration capacity. With this flowchart, we can perform our numerical validations. We use a commercial numerical simulator like Eclipse 300 to simulate the gas injection process. The global grid and the each cell's grids and the Flowchart grids we can show like here. Then we use some keywords like DIFF, CBM to consider the Knudsen diffusion. Also use some other words to consider the absorption stress sensitivity. Compare with the results between our model and the numerical simulators. We found the average difference is about 2.57%. It can be acceptable. Then we move the sensitive analysis because we want to know the impacts of some key factors on the storage capacity. Finally, we found that the storage capacity increases with the increase of stress sensitive coefficient and absorbed index like this, and the Knudsen diffusion coefficient like this. So we also found that the storage capacity decreases with the increase of storage ratio. This is high for storage capacity. Then we obtain some lessons. Finally, we end the case study. The case study is from a new Albany shells. The new area as shown in the figure. We obtain the well data and the reservoir data and some corn data. From this data, we want to estimate the capacity, storage capacity based on our method. During the estimation, we assume that the concentrated injection pressure is 7.2 because it's lower than the supercritical pressure of CO2. Also, it's below the rock breaking pressure in the reservoir. The rock breaking pressure reservoir is 8.5 MPa. After estimation, we found that we use the numerical methods and our methods and the semi-analytical methods. We compare that. We found that the estimated capacity is about 27 billion cubic meters, which is very promising. But we found that it only takes about 10 CPU tons with 100 ton taps use our method, analytical method. So it's very quick. Also, it's close to the estimate results is more close to the numerical method. So it's visible, which shows that our method can be acceptable. Then we end with the conclusions. The proposed approach is quick and reasonable. The CO2 storage capacity increased with the increase of stress sensitive coefficient, absorbed index, and Knudsen diffusion coefficient, and is decreased with the storage ratio. And the Knudsen diffusion coefficient increase. The effects on CO2 sequestration capacity is weak. Okay, thanks for the conference to report my paper. Also the paper for improving my work and the findings. Thank you. Thank you for your attention. Thank you.